Our objective for this lesson is being able to find the area between two curves. If you think of these streets as if they are curves that are being graphed on the coordinate plane, we just want to find the area of this strange region. Now, of course, in the last unit, the only thing that we were concerned about is finding the area underneath one curve bounded by the x-axis. So now we're taking it a step further, and let's say that we wanted to find the area between this top function, this f of x function, and this bottom one, this g of x function, in between a and b. Basically, I'm finding this strange region S. We want to find its area. All right, so I think that a good place to start is by approximating it with rectangles exactly the same way that we learned the whole entire integration process. So let's just draw one of these rectangles in here, and we call that thing a representative rectangle. I don't want to have to draw all of them in there. It's okay. I'm just going to draw one of them. And then I'm going to eventually turn this into a Riemann sum. Well, what are the parts of the Riemann sum? Well, you need a width, of course, and that width is delta x. We could do this whole b minus a divided by n in order to find that width. And now we also need a height of each one of these rectangles. And this is where that warm-up activity comes into play. So in that warm-up activity, I said, hey, we have ourselves a segment. We call it AB. What's the length of this segment? And it was basically the distance between these 2 points between those two curves, right? And one of the ways that we could do is just count it, or we could just take the top y value and subtract the bottom y value. And that's exactly what's happening right here. So remember that this x sub I is basically a random x value, some x value in the subinterval. It could be the left endpoint, it could be the right endpoint, or it could be any point that's in between here. It looks like this one chose the midpoint. Okay, so if I wanted to find the height of that rectangle, I just take that x value, plug it into the function to get the top y value, plug it into the function to get the bottom y value, and then subtract those two things. And there we have our height. Okay, so again, it's the top minus the bottom. And notice that we don't have to worry about the absolute value here because we want to focus on always doing the top function minus the bottom function. All right, we have height, we have width of our representative rectangle, and this is just to get an idea of what we're supposed to include in that Riemann sum. So the Riemann sum is going to give us a way to approximate the area underneath the curve, right? So we need to add up n of these rectangles, and that's going to look like this. So let's pretend like we have n of these rectangles right here, and so the area should be equal to, actually approximately equal to, because we're just summing up n of them instead of infinitely many of them. And here is our heights once again. And the heights are the difference between the top function and then the bottom function multiplied times our width. Whoop, whoop. So here's a question. If this is the approximation, what could I do to it to get the actual area underneath the curve, a better approximation? Well, I can increase that number of n for sure, and I can increase it as large as I want to by taking the limit as n approaches infinity. And then that is going to turn this into the actual area in between these two curves. So we have the limit as n approaches infinity. That's the number of rectangles gets obnoxiously large, and then that makes the width of each of those rectangles as close to 0 as possible. And I have this sum, the Riemann sum here. Again, it's the difference between the heights and multiplied times the width. So here's each one of those rectangles. Hey, I recognize that notation. That's a limit of a Riemann sum. And a limit of a Riemann sum is a definite integral. So I'm going to rewrite this thing as a definite integral from a to b of f of x minus g of x with respect to x. And I'm wondering, were you clever enough to figure that out without all of this explanation that, hey, maybe I think it just makes sense that if I wanted to find the area between these two curves, I'm just going to integrate the difference between these two things. We're going to see a series of pictures that's really going to help make this integral make sense visually instead of this kind of algebraic argument that we just made. Or is it really a calculus argument? Probably a combination of the two. Okay, so here we go. Area between two curves. And notice that I have my f of x function is the one that's on top, and we have the g of x function, which is the one that's on the bottom. And we're going to state that if f and g are continuous on the closed interval, and g of x is less than or equal to f of x, that's the fancy way of saying that the f of x function is the one that's on the top, and the g of x function is the one that's on the bottom. Then the region bounded by the graphs f and g and the vertical lines x is equal to a and x is equal to b is the definite integral from a to b of the quantity f of x minus g of x with respect to x. So remember that we have a property of integrals which allows us to break up the difference here. I've got two functions here, so I can break this up as the difference between two integrals, right? It's based on the summation property, which was basically the sum of a sum or difference is the sum or difference of the sums. So here, let me give you a visualization of this. Here's the area that we want to find, and we just stated that it's the definite integral from a to b of f of x minus g of x with respect to x. I'm going to break that up into two separate integrals, one for f of x and then one for g of x. Well, the definite integral from a to b of f of x gives us all of this area, all of this pink stuff here, underneath the f of x function. And of course, that's more than what we want, and what we want to get rid of is all this stuff that's here, which of course is the area underneath the g of x function. So that's the definite integral from a to b of g of x with respect to x. And like I said, maybe this was really obvious to some of you that are super clever, right? And then maybe this series of pictures really helps make this definite integral here make some sense. Okay, I'm going to make a suggestion, some pro tips for you in setting up each of these problems. And that is to draw in a representative rectangle. You have a graph of this, maybe sketch a little graph, draw in a representative rectangle like we have here. It's just one of them. You don't have to draw in all of them. Just draw in one of these little rectangles here with a height, your height being the top function minus the bottom function, and then we have our width there. And then you're going to turn that thing into a Riemann sum. And then you're going to take that Riemann sum and take the limit as n approaches infinity to turn it into a definite integral. And here's the reason why. There's a couple of things that I think this process is really going to cement for you. One of them is going to help you identify what is the top function versus the bottom function. Oh, here's another couple of pictures here. Top function versus the bottom function, right? Which may not always be obvious whenever you just have these things written out, right? So we have some sort of graph, sketch some sort of graph, put a little rectangle in there. It's easy to identify what the top and the bottom is. It's also really going to reinforce the definition of a definite integral as a Riemann sum, being able to convert between those two things. Because remember, if you have a Riemann sum on your AP Calculus exam, it is the idea of identifying the limit of a Riemann sum as a definite integral and then just evaluating the definite integral using the fundamental theorem of calculus. Okay, and the other thing that it's going to help us do is later we're going to take this rectangle and we're going to do some super special stuff with it involving some volume. So picture this ahead of time, just a sneak preview. What would happen if I took this rectangle that's right here, this representative rectangle, and I rotated it around the x-axis? It should generate a three-dimensional shape, and when it does, that shape is going to have some volume, and we can also find that volume using some integration, and that's going to come up in a future lesson within the same unit.